At the beginning, I think I need to mention that I'm just a co-author of this article because Dr. Kalush is a second author, and that's probably the only reason why I'm presenting this. He's a moderator, so he couldn't present this today. So, the topic of the paper I'm going to present today is predictive equations to evaluate thermal fracture of asphalt rubber mixtures. And at the very beginning, I just would like to make some short introduction about thermal cracking and what's the mechanism of the thermal cracking. And as we all know, the thermal cracking is always associated with the volumetric contraction of the material due to the temperature drop. And there are two cases, actually, what can happen with the material when the temperature drops. Every material tends to shrink, to shorten when the temperature drops down. So when we have an unrestrained material, like a kind of a free body material, when the temperature goes down, the material will shrink. All the stresses that could develop, thermal stresses that could develop in the material will go down. So finally, nothing will happen. Material will shrink, there will be no stresses, nothing will happen. But what's going to happen if our material is restrained? And that's the case with the pavement structure, because our pavement structure is a semi-infinite strip of the pavement, of the asphalt concrete material, which is in addition bonded to the lower layers of the pavement. So in this case, whenever the temperature goes down, the thermal stresses will be developing in the pavement. And that's a typical relationship between the temperature and the stresses that develop in the pavement. And the crack can start developing because the blue line now represents the typical trend, the typical relationship between the material tensile strength and the temperature. And what will happen when these two curves meet, which means that when the thermal stresses reach a level of the maximum tensile strength of the material, that's the moment when the crack will occur. That's the moment when the crack will initiate. And from this moment on, every other cycle, cooling cycle, will cause more and more crack. The crack will propagate. Basically, during my studies, I found more or less 7 different methods to characterize the thermal cracking potential. But basically, these 3 methods that we can see now are the most important and the most widely used in the literature. And the first method is the direct tension test. Basically, it's done on the cylindrical specimen. 2 plates, bottom and the top plate, loading plate, are glued to the specimen. The direct tension is applied, and basically the cylinder will break, and the maximum load will be reported. Next test is the thermal stress restraint specimen test, TSRST test. It's done on the beam-shaped specimens. The specimen is restrained in a loading frame, and then the temperature is gradually lower. And the moment when the specimen breaks, because it's restrained, it cannot contract freely. The moment when the beam break is reported, and then also corresponding tensile stresses will be reported. The third method, indirect tension test, that was developed during the SHARP program and along with the SuperPave method, is presently used in the mechanistic empirical pavement design guide that soon will become a new AASHTO design guide. And this method is utilized in the design guide to characterize the fracture properties of the material, of the asphalt concrete materials. And how the method looks like. What we can see on the picture is a typical loading frame with the specimen inside, and it's a 150 by 38 millimeters disc-shaped specimen. We can see on the picture, I know it's not very clear, but we can see 2 sets of the vertical LVDTs. They are on both sides of the specimen. We have a vertical and horizontal LVDT. During the test, what we can see also is an environmental chamber in which the specimen, the loading frame, is placed during the test. The IDT tests are actually, it's a set of 2 tests. First test is the tensile creep test, which is basically done in 3 different temperatures at 0, -10, -20 Celsius degree. And the test looks like this. We apply a static load. It's supposed to be small enough to not destroy the specimen, but high enough to produce a good signal. We don't want, during the test, to have too much errors. So static load along the diametral axis of a specimen is applied, and then the deformation that are measured during the test are used to calculate the tensile creep compliance as a function of time. Immediately after the creep compliance test, a tensile strength test is conducted on the same specimen, and a constant rate of vertical deformation to failure is applied, and we are using, this is according to the official protocol, we are using 12.5 millimeter, half an inch per minute of loading. And what we measure during the creep test, creep compliance test, we are doing the test in 3 different temperatures. So we're gonna collect the data, we're gonna build a 3 curves for 3 different temperatures, and then using a time temperature superposition method, we're gonna construct the creep compliance master curve. And then we're gonna feed a power model that we can see now as a form which is actually a function of no longer a time, because we use this superposition, time temperature superposition, but a reduced time. And as we can see, we have a D0, D1, and M, which is a slope of the creep compliance. And it's actually very, very important parameter that I will be discussing later. But this is right now probably the most important parameter that we have from the IDT testing. That's the M. Another test, tensile strength, we are calculating this using this equation. And basically, it's a function of a failure load, and is corrected for a dimension of the specimen, the thickness and the diameter. It also has this small correction factor, which takes into consideration the bulging that always occurred during the testing. Okay, and then the results from IDT testing become an inputs into the superpaved thermal cracking model that is now integrated part of the MEPDG, the Mechanistic Empirical Pavement Design Guide, in short TC model. And the first module in this model is a pavement response model that, based on the climatic files, climatic data, calculates what is the temperature of the pavement on different depths. And just to give an idea how it works, we are using hourly data of temperature, wind speed, solar radiation, and precipitation to calculate this. So this is a tremendous amount of data that can be used. And the data comes from the weather station, and an airport, and a special NOAA stations have this data. So there is a big potential of using this. So pavement response model gives us stresses due to the cooling. Then knowing the stresses due to the cooling, plus the properties of the material, as I said, the tensile strength at -10 Celsius degree, and M, which is the slope of the creep compliance, using the crack depth fracture model, we can calculate the crack propagation. So we will end up with the function of for every month, we're gonna have a crack depth that develop in this pavement. And then using the probability-based model, we can calculate what is the amount of thermal cracks per unit length of pavement. The focus of our study, of our research, was on this medium portion of the whole model, on the model that actually calculates the crack depth. There is nothing wrong as far as we find with the environmental model, and also the probabilistic model. It's simply mathematical model that calculates what would be the probability of certain occurrence of the cracks, certain spacing of the cracks, but everything based on what is the crack depth. So this is actually the clue of the whole model. This is the big processor that calculates what is the crack depth. So how this model works? The crack depth model uses a Paris law, which is described here. This is basically the change in the crack depth due to the cooling cycle is a function of the change in the stress intensity factor, delta K, and is multiplied by the 2 parameters, A, the power of N. They are very important parameters, especially A, and I'm gonna focus later on some modification to exactly this one parameter, A. And how is the A calculated right now in the existing protocol, existing method? We are using A that was, the equation to calculate the A that was developed by Molenaar. And According to this equation, A is a function of E, which is the mixture stiffness, but during the further calibration study that was done during the SuperPave and SHARP program, this A was fixed for 10,000. So right now, it's not anymore a variable, it's a fixed value of 10,000. So there are actually only two variables, ST, which is a tensile strength of the material, and N. And N, we can calculate using the Lighton studies and the equation developed by him, where N is a function, actually only a function of one variable, which is M. M, slope of the creep compliance. So what are the problems with the existing TC model? We find out that the existing TC model is able to properly predict the thermal cracking for conventional mixtures. But unfortunately, based on many studies from Arizona, we find out that it's not able to properly predict the thermal cracking for the rubber asphalt mixtures. And here is the example of this. When we used the laboratory measured data from rubber asphalt and conventional mixture, and when we compared them using the same structure, and we input everything into the mechanistic empirical pavement design guide, that's the result we get it. The red line represents the gap-graded asphalt rubber mixture, and the black line represents the conventional mixture, and we can see that after 10 years of exploitation, we get a higher cracking than compared to the conventional. This line would probably go higher, but there is a set limit, 2,112 feet per mile. It's a maximum, it's like a theoretical maximum amount of thermal cracking that can occur in the pavement. So that's why it reached this certain level and didn't propagate further. But the most important observation is that the rubber asphalt actually has higher cracking than the conventional mixture. And we know that it's not true, but that's what the state-of-the-art program is right now predicting. So there is something wrong with this. And we know that it must be wrong because we have many examples of a perfectly good pavements, and probably the flagship model and representation of this is the I-40 asphalt rubber projects that were done near Flagstaff in Arizona. And we can see from some characteristics, the conditions were really, really very harsh, like for the pavement. Temperature from -29 to 38 Celsius degree and elevation more than 1,700 meters. And after 10 years of service, of exploitation, the amount of transverse cracks was less than 4%. Okay, during preliminary investigation, we had some observation, and this is probably the most important one. As I said, during one of the IDT tests, the tensile strength test, we measure one value, we measure one parameter, which is tensile strength. But the truth is, it's not the only parameter we could get from this test if we properly analyze the data. I mean properly, if we just try to analyze more, take something, squeeze more juice from the data we are getting in the lab, we can actually get more results. And one of this is fracture energy, which is defined as an area under the load versus the vertical deformation curve. So what we can see here, this peak represents the tensile strength of the material. And what we can see, again, black is the conventional, red is the rubber asphalt. And we see that the conventional mixture has a higher tensile strength than the rubber asphalt. And why is that? It's because rubber asphalt is using more binder. We are usually adding much more binder than compared to the conventional. And besides of this, this mixture has these rubber particles that make the mixture more soft, make it softer, more flexible. So we will never get this as high stiffness for the mixture as for the conventional. So basically, it might crack sooner. But then what is important, we can see for the conventional mixture, after it reaches this maximum tensile strength, it's gonna crack immediately all the way through all the specimen. When for the rubber asphalt mixture, maybe the crack will initiate sooner, but then it's gonna propagate much, much longer. And how we can estimate this? By measuring this area, which is the total fracture energy. And as we can see, rubber asphalt mixture has more than twice as high energy when compared to the conventional mixture. So the conclusion from this is that tensile strength by itself is not the best indicator of potential for the thermal cracking of the mixture. There are also other parameters that could be used. Another problem, when we plot the creep compliance on in a log scale, we're gonna get this relationship. This line represents the creep compliance curve. And again, the color code, black is for conventional, red will be for the rubber asphalt. So that's how the conventional mixture, the creep compliance for conventional mixture will look like. When we compare this with rubber asphalt, we will see that, as I said, the most important parameter from the creep compliance study, from the creep compliance master curve, is M, which is the slope of the creep compliance. That's the parameter that is now used in the TC model. We're gonna observe from this that for the rubber asphalt, we have lower M value than for the conventional. Lower M value, basically, forgetting about everything else, the way the TC model thinks means worst mixture, so more cracking. And again, we know from the field study that this is not true. But the problem is that when we consider the existing method, we can't see the full picture. All we see is the M. M is lower, mixture is worse. But we need to look at the whole picture of this. And the whole picture says, when you compare these two curves, the upper one means that we have more compliance, creep compliance in the mixture. The mixture is softer, will deform faster, will relax more than the conventional mixture. So basically, it's better for the thermal cracking. And another parameter that we could use to better characterize this is a D1. We see that the rubber asphalt mixture has much higher D1. What does it mean? At the very beginning of the test, when we apply load, the mixture will deform much faster. Why? Because it's more elastic, because the rubber particles that are in the mixture are more elastic and will respond very fast. Conventional mixture is viscous. The rubber asphalt mixture is probably more elastic than viscous, so it's more elasto-viscous material, will respond much faster to the stresses that may develop in the pavement. And that's probably the reason why this M value is lower, because most of the stresses will relax at the very beginning of the test. So farther, we don't have so much stresses. So this M value is lower because there is not too much to relax after all. So that's probably why this M value. So again, in the existing methodology, we are using only this parameter. We should use both of them to have a whole picture of what actually happens over there. The focus of our paper was to develop the new predictive equation for the level 3 analysis of the design guide, and predictive equation for the 3 parameters that we would like to use further in our studies. The creep compliance, parameters D1 and M, tensile strength, and something that doesn't exist. These 2 predictive equations already exist, but we know they don't work very well for this. Another one, the total fracture energy, it's something completely new. It doesn't exist because it was not used by the TC model. The bigger goal, not of this study, but the whole big study that we are doing since a few years, is actually to develop a new crack depth fracture model that would be able to handle also rubber asphalt mixture, because as I just presented, the existing model doesn't predict the asphalt rubber cracking very well. So this development of a new crack depth fracture model is actually something like a bigger goal that we want to have. Just for appreciation how much work we did in our research, that we didn't develop everything overnight. I just want to present that we used 39 mixtures, which ends up with 351 specimens. And this includes 18 conventional asphalt mixtures and 21 asphalt rubber mixtures. And how the existing prediction equation works and looks like. This is the predictive equation for the creep compliance. And we are predicting 2 parameters, the D1, which is the intercept, and M. And we are predicting them for 3 test temperatures, for 0, -10, and -20. And we can see that the D1 is a function of temperature, air voids level, and VFA, and the A after RTFO. M is a function of temperature, air voids level, VFA, and penetration at 77 Fahrenheit. In this plot, the red dots This is a plot of the predictive versus measured creep compliance, and the red dots represent the mixture that were originally used in the design guide to develop the predictive equations, and the blue dots are the mixtures that we did in our study. And we see that they're not very far away, but they didn't really correlate like very good. So we decided to revise them, to modify them a little. We actually kept the same form of the model, but what we did, we numerically optimized them, so all the coefficients are different. And that's how the new model looks like. It has a little higher R-squared than the original model. We try to do the same with the predictive equation for the tensile strength, and this is the existing model for the tensile strength. Again, red line and red points represent the mixtures that were used in the original design guide development of the predictive equation, and the blue line and blue dots are from our mixtures. And we see that they also don't correlate very well. So again, we try to revise this by optimizing the model, and we see it's actually even worse. So we start thinking, okay, so what happened with this? One of the reasons for this is that our mixtures were all a lab-blended mixture with short-term oven aging, and the mixtures that were used in the original development of the predictive equation for design guide were all the way from 2 to 14 years old mixtures. So this could affect our study. So basically we decided to give up with these old mixtures and stay with ours. What I'm showing here is our results of the new model, but only for the first 9 mixtures. That's what we had at this moment. We are still developing and we are still improving our equations by adding a new mixture that we are still testing and doing. Finally, the new predictive equation for the total fracture energy. This is preliminary equation. We're still working again on this, and we are using the asphalt content, air voids level, the VMA, VFA, the penetration, and asphalt, and something that we call the rubber percentage in rubber content in the mixture. We calculate this by multiplying the asphalt content by the percentage of the rubber used by the volume of the asphalt content. This is how the new predictive equation, the correlation looks like, measured versus predicted. We can see that we have a very good correlation, very good R-square. What I wanted to stress here to make point is how important is this percentage of the rubber, because if we didn't use this, that's how our equation and that's how our correlation would look like. These points that are here are actually a rubber asphalt mixtures. So we really need this addition of the percentage of the rubber into this. What happens if we have conventional mixture? This simply becomes 0, but if we have a rubber, we can correct the original equation for this, and we can see how much better it works. At the end, something that was not actually a scope of this article and this paper, but something we are still doing, something we're still working on. This is some future directions. Again, Paris crack growth law, this is the main equation, and as I said, we now put our focus on this one parameter, the A, that is right now calculated according to the Molenar equation, and is a function of a tensile strength of the material, and N, which is a function of the slope. But there is also something else. This is an equation that was developed a long time ago by Shapery, and I know it looks scary. There is a lot of going on in this equation, but all I wanted to show you that you see what we have in this equation is the tensile strength. Again, I said that E, which is the stiffness of the mixture, has been fixed into 10,000 during the calibration process. So there are actually 2 variables, tensile strength and N function of M. In this equation, which is much more general and is more complex, but I really like it because it's able to handle more cases. We have tensile strength, we have M, slope of the creep compliance, but in addition we have also D1, so another parameter from the creep compliance, and the most important, we have a fracture energy. So all we need to do is try to utilize this equation. What happened here, the truth is that researchers, the Molenar, at the time when he was developing his equation, he knew about this one, and he was trying to simplify this. And the truth is that when you look at the creep compliance, when we compared the conventional and the rubber asphalt mixture, we saw that this D1 was, the difference between the D1 was so big. The truth is when you compare two conventional mixtures, I mean using two different binders, but conventional binders, you will see that the difference between D1 is not very big. It's almost the same. The only difference is M. So that was the philosophy behind this method. They decided because there is no difference between D1, it's not important factor, so let's not use it. Let's use only M. This is something important. But when we now went into the rubber asphalt mixtures, we find out that we really need this to see the whole picture. We need something more parameters. And the same with the fracture energy. So basically, what I see, we have two ways. We need a new models, new equations to properly analyze the rubber asphalt mixture. And the way I see this, we can develop completely new models that will work specifically and only for the rubber asphalt, or we can try to develop maybe a little more complex but more general equation that will be able to handle both conventional and rubber asphalt mixtures. And I think this second option is better because we can this way compare what is the difference between one and the other. If we will have two different models, one only for rubber, another only for conventional, there will be always quarreling like, you can use this because it's a different model, this is different equation. So that concludes my presentation. Thank you very much.
I was just curious what your thoughts are for using a fracture energy density as far as a performance test for fatigue cracking for rubber mixes and conventional asphalt mixes.
I remember at ASU we did some studies. There was actually one doctorate, one PhD done when other methods besides of this what we are using right now were used. And I remember that the energy approach was very promising. And that's all I know. I mean, I don't have more experience in that, but I did actually some studies, but I remember it was very promising. So basically that's what I observe is that this energy approaches in all performance models are right now like a very popular, and people are starting testing more and more this because they are bigger picture. They're showing not just the maximum strength of any other value, but like a brighter range of the properties, something more than just one value somewhere at a given temperature. So I think it's a good way to do this, but we probably need another few years to develop this. I mean, to not develop because it's already developed, but introduce this into the next generation of the design guide. So right now what we have is a state of the art, and now we're trying, like we're already thinking about the new generation, so another. I'm not sure if this answers your question or not. I think that it's a good approach. It's a good, very promising work, but as far as I know, it's still not inside, it's not implemented into design guide yet.
Okay, thank you.
Any other questions? Right here.
I saw a very interesting figure in figure 2. Can you go back to that the curve that you show for load deformation?
Is that one
yes.
you're talking about? Okay.
Thanks. Is this typical of all the mix that you tested?
Yes, of course. As I said, we did 39 mixtures. If I start analyzing one by one, this would be a long presentation. I'm sure nobody will appreciate this. This is something typical. And the truth is, it was actually kind of like conservative. I remember even much bigger differences in this. I mean, the mixtures, the rubber asphalt mixture that had twice as low strength, tensile strength as conventional, and still much higher fracture energy. So I didn't want to shock anybody too much because I know there would be a lot of talk about this. So I showed something that I think is conservative. We actually can observe much higher differences in this. And this, of course, affects the results of the predicted thermal cracking because, again, the lower the strength in the existing model, the more cracks we will have because that's how the model works. But the truth is, it's not really true like this.
I also noticed you see that the peak actually happens at the same amount of deformation.
Yes.
Is that also almost always the case?
They are very close. They're very close. They're not always so close, but they close. The truth is that usually for the rubber asphalt mixtures, we're gonna have this peak a little later. Especially when you go, you see, this is done only for one temperature. That's the result from one temperature because that's what we are using in the method also. Strength, tensile strength at one temperature at minus 10 Celsius degree. The bigger difference will be when we go to the lower temperature. When you go to minus 20, we actually observe much higher peak. It goes even higher for the conventional, but it will actually even occur sooner because the mixture is stiffer. At the same time, rubber asphalt still is soft enough to go slower with this, so it will not develop the stresses so high. So this shift will be higher for the lower temperature.
Thank you.
You're welcome.
One more question here. Yeah, it's okay. We started a couple minutes late, and we can take another question. Nobody's leaving too, so that's good. Good sign.
My question might be out of your research, but if there is cracking on the base or structure, and also before you lay the rubber asphalt 2 inches above, fiber mat or some type of fiber material, if you overlaid before you put down the rubber asphalt 2 inches, the friction or if there is any fracture around, would that be eliminated, or would your question will be changed, or your formulas?
You mean about the bound base, yes?
Not the bottom base, after the base. If you put some type of fiber mat.
I understand, but on top of the existing base that is cracked, yes?
Exactly.
There are different methods of treating this. Of course, you can put a mat, you can put a SAMI, something that will absorb this strains. There is a method also of crack and seed, just to not have this big concentration only in one crack, but kind of like mitigate this around the bigger area. So there is different methods, but of course the mats are one, the geogrids, and probably SAMI would be the best.
With the same asphalt mixture or different?
You mean the SAMI with the same
Yes.
asphalt mixture?
Are you trying to compare SAMI to the rubberized asphalt mixture? So I'm not sure what
No,
what's the
I
question
was
is.
trying to add that mat of fiber, and then what kind of characteristic would it have in the top?
Yeah, the stress concentration.
If there
will
is
be
any
different.
research also done on this aspect.
It will be a stress relieving layer, so the stress concentration will be different. It has to be treated accordingly.
Okay.
I saw another hand back there. I think we can take one more question. Yes.
Then I would just like to make an announcement because I may not have a chance and people may start leaving. For those that are vegetarian, please pick up the ticket before you go to the room, which is going to be here at the front. Also, there are going to be wine served, but you need to get the ticket for the wine. Now, for some reason, I apologize, it's beyond my control, but you, at the reception, please get the ticket for the wine. I don't know why I have to do it now during this break and not next break, but that's what they asked me to ask you. Sorry.
Thank you. That's all right, I got one.
Neat thinking, you know.
I just wanted to point out to you that Kirk Beatty at ASU in the early 90s, ISI sponsored some research, and he did fracture energy of beam specimens, conventional, polymer modified, and asphalt rubber binder. And he found that there were different groupings that you could identify and distinguish between the rubber modified, the polymer modified, and the conventional based on the fracture energy. So yeah, fracture energy has been around for a while, and it has been promising for a while. So I'm glad to see that it's finally being pursued a little further.
Yes, and as he said, we didn't discover here anything like especially new, but like this equation done by Sherpery is actually probably like 20 years old. We're just trying to come back. There is a lot of good potential in this. I mean, the problem was that it was changed to specifically feed very narrow range of the mixtures. And now what we want to do is just to expand this to use for generally the mixture.